Hi there, I'm Blair Johnson, and in this talk I'm going to tell you about some indirect effect size calculation strategies, how you could use p-values to get to inferential test values, and how you could deduce pooled standard deviations from information the studies give when they frustratingly don't give you the right stuff. I'll introduce you to the problem, which is overall that a lot of studies omit the relevant information that people need to calculate effect sizes. But the point is there are indirect methods to get to the goal. I'll tell you how to convert p-values into inferential statistics. I will show you how to use means to infer pooled standard deviations to calculate effect sizes. And in the end, I'll show how those two things can be used simultaneously. And I'll leave you with a couple of discussion questions. So, as you know, there's a direct calculation method to get to a standardized mean difference, SMD, which is generally an effect size, ES. So mostly we're looking for this idealized form over here, but we don't always get it. There are algebraically equivalent forms. If you've got a t-test comparing two effect sizes, you can get to the effect size this way. If you've got an f-test with two groups, that's important. You cannot use this for three group comparisons or four groups, whatever. It's only for the two group. Okay? And we can convert exact p-values from t-test or f ratios in order to convert into those things and then use the above equations. So here's how you would do it in Excel. What if you only have a p-value? You convert it to the equivalent t or f and proceed. So if you have a p for two group comparison that's reported as 0.1 p-value, and let's assume that's two-tailed. If it's 1, you'd multiply it times 2. And in this example, let's assume it's got 30 degrees of freedom, so n equals 32 in this case. In Excel, you put in what I've got here in column A is the probability value, and B, I've got the the degrees of freedom. So I've just copied those in. And then here's the equation in C2. So in Excel, if you type equals, you get a whole array of commands that you can ask Excel to do for you. And one of them is there's a whole array of these t-invert kind of things. It's an inverse t distribution. So you're plugging in a p-value, an A, that's this part, see the probability, and the degrees of freedom in B2. And it takes that information and produces an estimate of the actual t, which is right there, voila, when you let it go forward. So if you sketch the process forward, we've got our standard equation for the t-test to get to SMD. Here are all the values from above, just inserting them in, and you get the standardized mean difference. If you go out and use Dave Wilson's effect size calculator, you get exactly the same value. So it's comforting to see that things work out. Now, in a previous era, reports had everything we wanted. I mean, this was when things were really good. Back in the 1960 or so, when Edwin Hollander published this particular study, and the details are not relevant, I'm just pointing out, here's a whole analysis of variance table. Here are all the means as well in the displayed, so you could compare any two of interest to you. And here on the bottom of the analysis of variance table is a mean square error. And so as you know, you can convert that by taking a square root into a pooled standard deviation. I guess that tells you that an analysis of variance mean square error is a pooled variance, okay? But, you know, nowadays we don't get reports that give you all this information. So we have to do workarounds. Over years, editors decided we'll save space, and so let's just give the significant values, and they omitted all this kind of stuff. So we meta-analysts now have to deduce it. So that leads me into indirect strategies to calculate the effect size. And I'll refer you to the handbook chapter I wrote with Alice Egley. Here's a QR code for it that will lead you directly to a download. The appendix goes into these things in great detail. So we're going to assume the between groups ANOVA strategy here and examine mean differences between groups. And I've already said the mean square error will give you the pooled standard deviation. So we know from the logic of analysis of variance that a mean square error is going to be defined the mean square error is in the denominator, and the mean square effect is in the numerator. And that implies that if there's any f that's reported and you've got the means available, then you can deduce the pooled standard deviation. And then you can go ahead and use the pooled standard deviation to compare any two groups' means to get to your SMD. So this whole logic, which is basically present in the analysis of variance summary table, it's hard to see it here because I didn't animate correctly, but you get the idea that these are all strung together, it's all proportional, you can do this. All right, so let's take an example. Here's a 2x2 design. You don't have the right F, like you really wanted to compare the treatment and control groups, but the report didn't do it. Darned authors, it's like herding cats. We know that it's a factorial design, so we've got 40 people in each of these cells. You really want this comparison between treatment and control, or maybe you even want it within gender, if your hypothesis concerns gender. But all you know is that there's a gender F value of 4.29, and you have all the means for this 2x2. It's been well reported, at least in terms of its means. As study authors, whoever is watching this video, report all the details like this, because then a meta-analyst can work with it. Okay, so we're going to start with the gender effect to deduce the actual pooled standard deviation. Okay, so here's the logic. Go ahead and calculate what the gender effect size is. So now you're comparing these two means over here instead. And that's going to allow us to get to the standard deviation because you know of all the equivalencies. So here's the equation for F. There's the detailed information being popped into the relevant spots. That creates an SMD of 0.33 roughly. And we know that's equivalent to this. So the pooled standard deviation is in there. We just have to get it out. Now you just have to solve for the pooled standard deviation because this information is already known from our table. We've got the relevant means, the relevant means over here. So all we have to do is compare them in this equation and solve algebraically, and we've got it. I've done it for you here. So here I've inserted the means, here's the difference between them, and then you've got to flip them around in order to get this, to deduce what the pooled standard deviation is, and it turns out to be this value. So now you can use that value to calculate the effect size of interest. If it's the comparison of the treatment and control overall, then away you go. Right. Now, Dstat will do all that work for you. And I described in a separate talk how to install Dstat. It's antiquated software, but it still has some pretty cool procedures in it. So some procedures there are still worth using. And if you don't have a copy of Dstat, send me an email and I'll make it available to you. So in Dstat, I'm starting from either the F menu or the means and standard deviations menu, and I'm going to the different but related function in there. You'll see it. Trial and error, you can find it. And I'm entering all the relevant information. I've got two groups in there. There's 80 in each. Here are the two means. There's the F value. And then it produces the information you need. There's that standard deviation again. In fact, this is the very same effect size we calculated a minute ago. And now you can use that standard deviation again to calculate any difference of means you want. Okay. Note as well that this widget is very useful for one-way ANOVAs that have more than two groups. So when you run into that problem where there's 3 or more groups compared, this one will help you. Now, you could do the very same example I just did using the full factorial, the 2x2, and deduce the relevant F and standard deviation using Dstat again. So here it is step by step. In Dstat, you've got to annotate what's going on. So we're going to tell it how many variables we've got. In this case, 2. And let's label the dependent variable. If you have multiple output from a study where you're doing calculations, it can help to have more detail. It's a treatment effect and a gender effect. We give it labels for the two groups. So the treatment one has a treatment and a control. The gender one has males and females. And then we're entering an F value, in this case for gender. Of course, it could be any of these other things. I'm not sure I'd advise using this one, number 9 on that list. But if you were sure you've got the right dependent variable, you could try it, okay? That's probably a good discussion question right there. Here are all those means that appeared on the prior pages. And now, voila, you produce the ANOVA summary table. And it has exactly the same pooled standard deviation as the prior calculation. And now you could take that value and calculate your intervention effect if you wanted. Or if you could just go directly from this F value too. They're equivalent. They're exactly the same algebraically. And then, as you probably picked up when I showed you the example, the Dstat routine will allow you to go as big as a three-way design, and it doesn't have to be limited to 2 levels in each one. I forget how high it will go on that, maybe 10 different groups, something like that. So the strategy is the same if you must estimate F from a p-value. So then you're just combining the 2 strategies that are in this talk. So you're going to deduce the F from the p-value, then deduce the SD pooled. Obviously, if the p-value is very exact, this should be equivalent to the exact result that you get from the F if they reported it that way. And to the extent that it's imprecise, like a level p, 0.05, which is worse than, say, describing an effect as 0.001, you're going to have accuracy suffering. And usually that's going to mean the standard deviation you derive will be larger, and therefore effect sizes will be biased towards 0. So noise will make your effect size smaller. Now, this is maybe the big conclusion from this, although the discussion question maybe has an implication that we can come back to when we talk together. But greater availability of software and expertise to use it would enable more studies to be incorporated in meta-analysis. So obviously the strategies I'm talking about here in this little talk merit use and should be used, and that's why I'm going through it now and recording it. So I'll leave you with a couple of discussion questions. First, what do you think are the consequences to a meta-analysis when effect sizes cannot be derived because the studies have insufficient information? We call these like impoverished reports. They just don't have the essential information you need. So what's going to happen to a meta-analysis if you can't get these impoverished reports into the meta-analysis, or you can't get them to be exact enough, which is a related problem? And are there any other problems to these imprecise statistics that appear in source studies? I suppose one ramification should be, as a primary level researcher, report the stuff that a meta-analyst would need. It's going to save you trouble in the long run, and your study is going to be more likely to be included in relevant meta-analyses over time. So again, I'd recommend it. All right, thanks for watching my talk. There's my contact information. Have a great day.